A card is selected from an ordinary pack of playing cards. Presumably, we are dealing with a random selection here. Now, in the previous video, I said that a random selection usually means that every card has the same probability of being selected. There are 52 cards in a pack of playing cards, so the probability of any one card being selected is 1 over 52. So that's what we're assuming here. What are the probabilities of the following being selected? A black ace. Well, there are 2 black aces in a pack of playing cards, the ace of clubs and the ace of spades. There are 4 aces altogether. The other 2 aces are the ace of hearts and ace of diamonds. The ace of hearts and ace of diamonds are red. So we want the probability of this event, selecting a black ace. So how many elements are in this event? Well, we can see that we have 2 elements in this event. So if you can imagine the sample space of all outcomes consists of 52 cards, 52 equally likely outcomes. And this event here is a subset of the sample space. We put the number of elements in this event, which is 2, over the number of elements in the set of all equally likely outcomes, which is 52. This simplifies down to 1 over 26. Now, what about the probability of selecting a 2 or a 3? So how many 2s and 3s are there in a pack of playing cards? Well, there are 4 suits: clubs, spades, hearts and diamonds. So we have 4 2s and we also have 4 3s. So we could have the 2 or the 3 of clubs, spades, hearts or diamonds. So we're dealing with an event that consists of 8 elements. So the probability of getting a 2 or a 3 is the number of elements, which is 8, divided by 52. Well, we can divide above and below by 4 here. 4 2s are 8. 4 into 52 goes once, and 1 over 4 3s are 12. Now we could arrive at this answer using the OR rule, which was discussed previously. We could get the probability of getting a 2 and add it to the probability of getting a 3, because we're dealing with mutually exclusive events. So we could consider 2 events. One event would involve getting a 2, and this event contains 4 elements, because we have the number 2 for each suit: clubs, spades, hearts and diamonds. And then we have a second event which involves getting a 3 of each suit. So there are 4 elements in here: clubs, spades, diamonds and hearts. And I can write that 4 in square brackets to indicate the cardinal number, or the number of elements in this set. These sets are disjoint, so that means they're mutually exclusive. If we get a 2 of some suit, that excludes getting a 3, and vice versa. So anyway, the probability of getting a 2 is the number of elements in here, which is 4 over the total 52. The probability of getting a 3 is 4 over 52. And by the OR rule, the probability of getting a 2 or a 3 is 4 over 52 plus 4 over 52, which is 8 over 52. So we add the probabilities when we're dealing with mutually exclusive events. If the events weren't mutually exclusive, we would have to subtract off the probability of getting the event which consists of the intersection of these 2 events. The intersection of these events here is the null set. The probability of the null set is 0 because there are no elements in it. Anyway, it's probably easier just to count them up using the first approach. Next, we want the probability of getting either an ace or a king. So again, we could use the OR rule. We could get the probability of getting an ace, which is 4 over 52, because there are 4 aces in a pack of cards. The probability of getting a king is 4 over 52, because there are 4 kings, king for each suit, clubs, spades, hearts and diamonds. These are mutually exclusive events, getting an ace or a king. If the outcome is this event, getting an ace, then it cannot be this event here, getting a king, and vice versa. So we're dealing with mutually exclusive events. That means we can sum the probabilities if we want the probability of an ace or a king. So we 4 over 52 plus 4 over 52, which is 8 over 52. However, it's usually just easier to count up all the required outcomes. We have 4 aces and 4 kings, so we have 8 required outcomes. 8 distinct outcomes. So the probability is just 8 over 52. If you were asked what is the probability of selecting a club or a 7, how would this differ from the probabilities asked for in parts 2 and 3? Well, the events getting a club or getting a 7 are not mutually exclusive events. We could draw a Venn diagram to represent the event getting a club. How many elements are in this set? Well, in a pack of 52 cards there are 4 suits. Clubs is one of the suits. 52 divided by 4 is 13. So there are 13 clubs in a pack of 52 playing cards. So I'll put the number of elements in this set in square brackets. We would have 13 dots in this set representing each club. We would have the ace of clubs, 2 of clubs, 3 of clubs, up to 10 of clubs. Then we would have the jack, queen and king of clubs, giving 13 altogether. Let's look at the event getting a 7. Now, these sets are not disjoint. That means there is at least one element in the intersection. How many 7s are there in a pack of cards? Well, we have 4 suits, so there are 4 7s. We have clubs, spades, diamonds and hearts. So there are 3 elements in this region, but we have 1 element in this region. This is the 7 of clubs. So let's just show the elements here. I won't write them in, of course. Each dot represents a card. We've 1 here in clubs, so we must have 12. Okay, so 13 dots inside this circle here. 4 inside this one. So the events club and 7 are not mutually exclusive, but to get the probabilities of getting a club or a 7, well, that's just the union of the 2 sets. Actually, we don't even have to use this rule for the OR operator, because we can just count up the elements. We have 13 and 4 is 17, but we take 1 because this one has been counted twice, so there are 16 elements. So all we do here is put the number of elements in the union of both sets over the total number of elements in the sample space, which is 52, because we have 52 equally likely outcomes, so we can do that. But we can also use a rule here which says that the probability of one event or another event is the sum of the probabilities of the 2 events minus the probability of the intersection of the 2 events. So the probability of getting a club is just the number of clubs divided by 52. Well, there are 13 clubs. The probability of getting a 7 is the number of 7s, which is 4. 1 7 for each suit. Over 52. And then we have the probability of getting a club and a 7. Well, there's only 1 element in this event. You can see it here. This set here is the event club intersecting 7. It's the intersection of these 2. We just have 1 element in it, and we put that over 52. And of course we get 16 over 52. But in the question we're just asked to explain how this this new probability differs from the probabilities as for in the previous parts. So you only need to state that these two events are not mutually exclusive. Well, I've actually already answered part B. Here's the set of clubs. Here's the set of sevens. Now I haven't written in the names of each element. Let's see now. If I select a card from an ordinary pack of playing cards, what is the probability that I select a club or a 7? Well, I've already answered that. So that's 16 over 52. A club and a 7. Well, I mentioned that already. It's 1 over 52. Well, this question should really say, what is the probability that I select the 7 of clubs? Okay, we're selecting just one card. The way this question is phrased, it looks like it's asking for the probability of selecting 2 cards, but this is really just the 7 of clubs. Next question, we want the probability of selecting a card which is neither a club nor a 7. So what we want is the number of cards that are neither clubs nor 7s. We know that 16 cards are either a club or a 7. So the remainder of the 52 cards must be neither. So we have 52 minus 16 divided by 52. That's 36 over 52. If we want to use the language of sets here, we have the number of elements that do not belong to the union of clubs and 7s. So let's look at the union of the events getting a club and getting a 7, and we take the complement. That means everything outside of this set. We want a number of elements outside of this set here, clubs union with 7. And of course we put that over the number of cards in the sample space, which is 52. What is the probability that if I select a card 3 times in a row, each time replacing the card will be a club or a 7 for the first time on the 3rd trial? So we're dealing with independent trials here, because each selection is a random selection. And we replace the card each time. So the probability of selecting any card in each trial is 1 over 52. So, the probability of selecting a particular card on the 2nd trial is not affected by the probability of selecting a particular card on the 1st trial. It's not affected by what the outcome of the 1st trial was. So after the 1st trial, that means the 1st selection, the card is replaced. And in the 2nd selection, we presumably have a random selection, so it's 1 over 52 for the 2nd selection. So the result of the 2nd selection is not affected by the result of the 1st selection or trial. Similarly for the 3rd trial or 3rd selection, the outcome is not affected by the first 2 trials or selections. We could call this process sampling with replacement. By sampling means a trial, a selection of one card in this case, and the card is replaced in the pack. So this is the situation. For the first trial, we want the card to be neither a club nor a 7. What's the probability of that? Well, that was answered in C part 3. We got 36 over 52. For the second trial, we want the card to be neither a club nor a 7. We're dealing with independent trials, so the probability that the second card is neither club nor 7 is also 36 over 52. For the third trial, we want the card to be a club or a 7, and we've calculated that probability already. It is 16 over 52. So these are the probabilities of each trial. Well, the probabilities for the particular event of each of the 3 trials. These 3 events are independent, and as we saw in a previous video, to get the probability of the combined set of events, we multiply these probabilities together to get a much smaller probability, of course, than any of these three. To 4 decimal places we get 0.1475.